Thanks a lot from my side for the organizers. I'm very happy to be here. I learned a lot over the last 2 days. I'm not an expert in Kleefstra syndrome, so that was really very educative for me. So today I would like to talk about 3 topics. How can AI support physicians in diagnosing Kleefstra syndrome? Well, I mean, we heard a lot about AI, so I focus on the image analysis of portraits. What do computer scientists need to improve such kind of AI, and how could patients and families contribute? So who is a Trekkie? Who knows this device here? Okay, cool. I'm not the only one. So it's basically how we do diagnose in the future, right? Or do we really wait? Do we really have to wait for the future? Can we do it now? I think we can. And let's revisit a little bit what has happened. So in the last decades. So about 8 years ago, the first paper with deep convolutional neural networks that are used for portrait identification was published. And this is the technology that resulted, for example, in Face ID, the technology that unlocks our phone, right? That just took 2 years for rare diseases, which is a niche. It took a little bit longer, but in 2019, that was basically the foundation of Deep Gestalt, the algorithm that some of you might know from Face2Gene, the web service. And then in the same year, algorithmic advancement was published, which is ArcFace. I will also talk a little bit about how that resulted further developments of facial syndrome recognition. So who of you is not aware of Deep Gestalt or that web service? Or I don't know whether you're too tired or whether all of you know it, then I can skip that. So basically, you can question a portrait, right? And this will list potential differential diagnosis. And the more frequent that syndrome is, the better it will work in that tool, because it basically has to be trained in advance to recognize this syndrome. So for Kleefstra, it works. This is a disease I particularly know. The second one, Mabry syndrome, but sometimes it doesn't work, right? So what's the main reason for that? So if we look at the frequency of these disorders, or the incidence, or rough estimates for the incidences, simply by going to ClinVar and checking how many pathogenic variants have been submitted for this disorder, then we see the explanation. So the more data we have, the easier it is to support it. Okay, but what do we do if we have a highly recognizable facial gestalt, but just 2 individuals? And let's take this as an example. So what we do, we still process it through that network. That's just a sketch, right? We need many layers. And that network was trained by known disorders, Kleefstra and others, for example. And then we basically use the coordinates that are defined by the values in the penultimate layer. That's the feature layer, right? And in our case, that's a 320-dimensional vector. So here you see projection into 2D. So lots of information is lost, but the basic idea is still the same. So if you are close in this facial phenotype space, that means you are similar, syndromically similar, and we basically argue then it's likely that you also have a high chance of having the same molecular cause of your disorder. Okay, so that is the basic idea of the Gestalt Matcher approach, which allows you to match not with disorders, but single cases. Okay, and from the beginning of this year, this is a paper from Alexander Hustings, a PhD student in our lab, and he tried to combine both approaches. So it's called a model ensemble. That means he combines basically what's working well in general face recognition with that of rare and ultra-rare diseases. And just to show you how impressive these performance gains can be if you exchange the architecture, the underlying architecture, but still work with the same data. This is the main result from that work. So in the first line, you basically see the performance that was achieved for the old architecture, the Gestaltmatcher paper from 2020. And then on the bottom line, you see what you achieved just by replacing the architecture by ArcFace and introducing this ensemble approach. So this is a tremendous improvement in the performance. So that we always use the top accuracy rates as readout, right? We check from a test set that the AI didn't see, how often did the correct diagnosis make it to the top position or the top 10, and basically here the improvement would be from 16 to 53%, or from 19 to 36%. Okay, now I'd like to quickly talk a little bit about work from Hannah Klinkhammer. So she can make a contribution to the lumping and splitting problem. So whenever, what's that problem? If some faces look similar or diseases look similar, can we assign them to a phenotypic series? Ideally, because also on a molecular level, they are caused by deficiencies perhaps in a molecular pathway, or does the phenotype look so different that we should split it into different classes, and perhaps this is telling us something also about different molecular mechanisms. And I just show you how this looks like in the clinical phase phenotype space. So first I showed you a projection to 2D of this high dimensional space, but if we work with the distance metrics, that is basically the original information, right? So this is now the distance metrics, or a subset of this distance metrics, where I color-coded the similarity or distance. And now you can see that we do see certain clusters or outliers of these clusters. And now the question is, how different do these clusters need to be so that we can make a decision about splitting or lumping? And I'd like to show you a pleiotropic gene some of you might be familiar with. It's SMARCA2, and we know that two different episignatures do exist. Can you also see the difference in the facial phenotype? Maybe some people in the front. One feature that you see only in one half, but not in the other. Okay, maybe it's, anyone wants to say something? The distance between the eyes? Yeah, okay. I think that is pretty much the location where we should look at. So let's ask Gestaltmatcher. That's basically how he would do the grouping. And we do see that the eye region is basically what can be used as a feature for clustering. And on the one side, we have the blepharophimosis, impaired intellectual disability syndrome, and on the other side, the Nicolaides-Baraitser syndrome. Okay, so this is basically how we work, right? So we can use the distributions of the distances in inside a syndrome class or in between syndromes. And then we have to find basically a suitable threshold to make a decision about lumping and splitting. And and what I just showed you for SMARCA2 is a very clear decision. Here you basically see the two groups, the distributions of the distances for the two groups in yellow, and that is very much on the side of splitting. So if we do that for everything the ClinGen task force already did over the last few years, we can reproduce most of their decisions just based on the portrait phenotype. And obviously, they also work with additional information. So not all of those that we could reproduce are problematic, because sometimes they don't even have information in the portrait. Okay, so again, as a research tool, and maybe I know too little about Clavestra still, but in some of your talks, I really thought about maybe some of the variants also result in different phenotypes. Maybe we can discuss about that later, but it could be analyzed basically. And I just show you shortly for a new gene that will be published soon how clear this clustering can be. So in this case, the researcher said, the clinician scientist said, to our opinion, this two phenotypes in this gene look different, and then we could reproduce that by Gestaltmatcher, and they clustered into the two different exons. It's a gene with just two exons, and then later on, episignature analysis also showed different profiles, and on the molecular level, probably mutations in exon 1 are loss of function because the product is decayed, and in exon 2 it escapes nonsense mediated decay, and it's probably a gain of function. So here it's now almost a complete story. Okay, how can these scores also be used for making a diagnosis in a test case? So think again about these thresholds and distributions. So if we basically are able to assign most of the Clavestra cases to the Clavestra group and have only very little dilution by non-Clavestra cases, we can compute the positive likelihood odds ratio. I did this here just with the data that we have in the Gestaltmatcher database. And this ratio could also be used to upgrade, if it's possible, this PP4 criteria in the ACMG guidelines that work with the phenotypic information, right? So right now, standard is to assign it supportive evidence. But if the facial phenotype is very distinct, we could upgrade it to moderate or strong evidence. And for that, we need more data. That is now the last part where the patients can contribute. And the data needs to be findable, accessible, interoperable, and reusable. So we try to implement that in the Gestaltmatcher database. So you're all welcome to use it. And maybe for some clinicians, it's helpful also if they want to find quickly other syndromic data here. And if you, so we don't have enough Clavestra cases yet, so that would also be highly appreciated. So interoperability also means to share the data, if possible, with other groups. That's what we do. That's why we are part of the Matchmaker Exchange Network. And I would like to stop here and happy to take questions. And if you don't have a Gestaltmatcher account yet, you can also take a picture of this QR code, and it will help you to sign up. Okay, thanks a lot.
Okay, thank you, Peter. Questions?
So we had a couple of VUSs that we weren't sure what's going on in there, and we thought, let's try AI. And the AI result was that on a facial signature between KMT2C cases and controls, it was in between, so also VUS. So we ended up, thank you, that was useless. So because these milder cases might have milder phenotypes, so how do you deal with this? I'm just curious.
Yeah, I mean, that's what I try to show with the Bayesian framework, right? Not every gene phenotype is highly characteristic. So I think I would need more KMT2D, no, what was it? To see data to analyze it again. But maybe there the supportive level is the correct one, right? Maybe we cannot go higher.